There we go. Okay, perfect. Here we are, precipitation reactions. You can even see my chicken scratch from the last lecture on my writing on here. And like I said, I have a video on my YouTube channel that already covers this section. But let's go over it. It says here, in a precipitation reaction, two soluble ionic compounds, both would be denoted by AQ. Okay, so two soluble ionic compounds are going to react to produce an insoluble product, and we call that product a precipitate. The way that you know something is insoluble when you're looking at your reaction is because if it's insoluble, we follow it up with S, which stands for solid. So say, for example, you take these two homogeneous, clear, colorless solutions and you mix them, you end up forming this yellow precipitate down here. And I think that precipitate is probably lead 2 iodide because it's a really bright yellow. And we would denote that it's a solid by putting the S in brackets after it like that. It says here that it is possible for more than one precipitate to form in such a reaction, but we can only get two precipitates or more if we have more than two aqueous reagents. Anyhow, let's move on. And we already covered this slide, so I'm going to move past that. And I just want to talk about how do we predict when we're going to get a precipitate. Well, the first thing you're going to do is you're going to look at all the ions that are present in the reactants. In order to be able to do that, you've got to know your nomenclature frontwards and backwards, and you have to know your polyatomic ions, okay? So we could even pencil that in here. You need to know nomenclature very well, and you need to know your polyatomic ions, of course, to master your nomenclature skills. Then you're going to consider all the possible cation and anion combinations that you could make, and then you'll go to the solubility rules table to decide whether you're going to get an insoluble or a precipitate at all, okay? Now, the solubility table, this is kind of where we left off last class. And I went over this a little bit, and I said, you basically take your ionic compound, and then you use this table to help you determine whether or not, something is going to be soluble or insoluble. And so we would use this table. And the thing is that we're going to use this table several times today. So we're going to come back to this table. And that's why I'm erasing all this spinach that I have on here. Well, let's say, for example, we had this compound. I'll just show you one more time. If you had this compound, this is called lead 2 iodide. How do we know that that would give us a solid? Well, if we look at the table and we start on the left-hand side and we look at soluble ionic compounds, it says here that all common chlorides, bromides, and what? Iodides are going to be soluble. Well, hold on. We have to go over to the exceptions because on the right-hand side, we have insoluble exceptions. And it says that if you have a silver, a lead, a copper, or a mercury salt of an iodide, it's going to be insoluble. And look at this. We have lead 2+, and that's what's found in this compound. And that's how we know that lead 2 iodide is a solid. Okay, so that's basically the crux of how we use the table. And again, we'll use it a couple other times today. So I'm going to erase this spinach. Now, a very astute student asked me, do I have to have this table memorized? The only part that you have to have memorized are the parts highlighted in red. So memorize what is highlighted in red, okay? The rest of it, all of this, I would give you on a test, on an exam or a midterm, okay? So you wouldn't need to have that memorized. And if you're wondering, oh man, I got to memorize some rules. Well, you know what? Having these rules down pat is very handy. And in fact, I have a second version of this exact same table where they put these two rules together. I'll show you over here. It's the exact same table. It just sandwiches. It puts the ammonium in with the alkali metals like that. Anyhow, I'm probably just going to refer back to the first one. But again, we want you to memorize the first rules 1 and 2. If you go back here, it's rules 1, 2, and 3. Okay. Anyhow, let's keep moving and talk about what's called a metathesis reaction. And a metathesis reaction is another name for what's called a double displacement, or sometimes they even call it a double replacement reaction. If you took high school chemistry, you may have been exposed to these as double replacement reactions, but you might not have heard of a metathesis reaction. So metathesis reaction It says here when we take sodium iodide, aqueous sodium iodide, and we mix that with lead-2 nitrate, we end up with lead-2 iodide, which is the solid. Okay, we just looked at the solubility table and determined that that was a solid. And you get sodium nitrate. Okay, now all of these other compounds, sodium iodide, lead-2 nitrate, sodium nitrate, those are all soluble, and that's why they're followed up by AQ, right? That denotes that they're all soluble compounds. Now, this equation that we have written here, this is called our molecular equation, or yeah, our molecular equation. What we're going to do next is we're going to break this up into what's called a total ionic equation. And what you do in a total ionic equation is everything that's aqueous, all three of these things that are aqueous, we're going to break them apart into their ions. So what's sodium iodide? What's it made of? It's made of 2 sodium ions and 2 iodide ions, right? What about lead-2 nitrate? What's that made up of? It's made of a lead-2 ion and 2 nitrate ions. Okay, good. And what about sodium nitrate? What's that made of? It's made of 2 sodium ions. Is this not balanced here? Yeah, there should be a 2 here, shouldn't there? Well, there, fixed it. Okay, there should 2 sodium ions and 2 nitrate ions, like that. Okay, now if you're wondering what's this other equation that you have down here at the bottom, Mr. Dan, well, funny you asked. Okay, this equation down here, we call this the net ionic equation, the NIE. And what we do is we cancel out any ions that are not involved in the reaction. Now, what's the actual reaction, right? There is a reaction taking place, and it's the reaction to form the solid, right? These ions, look at the sodium ion. It's a 2 sodium ions here and 2 sodium ions here. Was that affected? No. And so we cross that out. That's what we call a spectator ion. If we look at the nitrate anion, look, we have 2 nitrates and 2 nitrates. Was that affected in the reaction? No, it didn't do anything. Okay, so we cancel those out. Those are called spectator ions, and we're left over with our net ionic equation, which is shown here. So overall, the net ionic equation shows us what the heck actually happened to produce this precipitate. All right, so it says here that ions exchange partners and a precipitate forms, so there is an exchange of bonds between reacting species. All right, let's move on. It says here predicting whether precipitation occurs. Let's just look at one of these examples since I have the other one solved in a video on my YouTube channel, but we'll look at the first one. It says predict whether or not a reaction occurs when each of the following pairs of solutions are mixed. If a reaction does occur, write a balanced molecular equation. So that's the molecular equation, the ME, a total ionic equation, and write a net ionic equation for these reactions and identify any spectator ions. So we're going to start with this one here, potassium fluoride plus strontium nitrate. So by now, we're in the 3rd week of school. It's Friday, so at the end of the 3rd week. Next week is the 4th week of school of what is a 16-week semester. I mean, besides finals week, but it's a 16-week semester. And so next week, we're going to be a quarter of the way through the entire semester. And so by now, you've got to be able to say, okay, potassium fluoride. Potassium has a charge of +1. Fluoride has a charge of -1. So there's the formula of potassium fluoride. Strontium nitrate. Strontium is an alkaline earth metal. It's got a charge of 2+. Nitrate is a polyatomic ion that I memorized. It has a charge of 1-, so that means I have Sr, and then I need to have 2 nitrates. So you need to be able to come up with those formulas. So now we know that we've got potassium fluoride plus strontium nitrate. Well, let's move over here, okay, and we'll write the whole thing out. So what's going to happen is that we have potassium ions, we've got fluoride ions, we've got strontium ions, and we've got nitrate ions. Now, in this reaction, this is a metathesis reaction, and the cations and the anions are going to swap partners. Remember, this is plus, this is plus, this is minus, this is minus, so they are going to swap partners. So we're going to end up with potassium nitrate. So let's write that down. We're going to have potassium nitrate, okay? I'll avoid the solubility, okay? And we're also going to end up with strontium fluoride. Now, Strontium has a charge of 2 plus, and fluorine has a charge of 1 minus, so it's going to be SRF2. Okay, we need to balance this bad boy out. So you can see that it's already done for you on the slide, but let's just give it a shot here. We've got 2 potassiums here, so we need to at least have a 2 here. Now the nitrates are balanced out. We've got 1 strontium, 2 fluorines. We're good. So now we've balanced it. Now we've got to ask ourselves about these 2 ionic compounds, potassium nitrate and strontium fluoride. Okay. Nope, I didn't mean to do that. Paste. I meant to do copy. There we go. So now let's go back, all the way back to the solubility table. My solubility table. There we go. Paste. Okay. Let's look at these 2 compounds. The first one, potassium nitrate. It says all common compounds of group 1A that have potassium, no exceptions. And so potassium nitrate must be soluble. What else? It says here strontium. Oh, jeepers. Let me find strontium. There's nothing in here about group 2, but I have fluorides. It says here all common fluorides are... Don't tell me it all got deleted. Guarantee you it all got deleted. Yeah. Okay. So we had already determined that potassium nitrate was aqueous. I go over to fluorides. It says that all common fluorides are soluble except for lead-2 fluoride and fluorides of group 2A. Well, strontium is found in group 2A. So that means that strontium fluoride is a solid. So now we can go back to our equation. Okay, and by using the solubility table, we were able to say aqueous and solid like that. So what's happening in the total ionic equation then is that we're breaking up everything that's aqueous, potassium fluoride, strontium nitrate, and potassium nitrate, into all of their ions that are shown here. The only thing that we don't break up into its ions is the strontium fluoride because it is a solid. What do we do next? We're going to cancel out any ions that don't participate in the reaction. Well, if I look at my potassium, it remains unchanged on both sides of the equation. If I look at my nitrate, it ends up unchanged. And so in my net ionic equation, I'm going to put that I have strontium plus 2 fluorines gives me strontium fluoride solid. And that is my net ionic equation. So you've got to be able to do a question like this. I told you I wasn't going to do the next one, but I'll just kind of walk you through it quickly here. It says if you take ammonium perchlorate and sodium bromide and you do a double displacement reaction here, this is actually kind of a funny one because you end up with ammonium bromide. If you look up ammonium bromide in the solubility table, you'll find that it's soluble. Okay. Then you're going to combine sodium and perchlorate. So you end up with sodium perchlorate. And that, when you look it up at the table, it's also soluble. Okay, so everything in here is soluble. When you write out your total ionic equation, literally every single thing in there should be canceled out. Okay, it says here that every ion is a spectator ion, so there's no net ionic equation. And you're like, oh, Mr. Dion, that's a trick question. It's not a trick question. It's just telling you that if everything remains in solution, there's no reaction. Nothing happens. All right, give me a thumbs up if you follow me thus far. Just on solubility table, metathesis or double. Thanks, Matthew. Perfect. All right. Thank you, Liv, Blake, the gang. Good. Great. Excellent. Well, let's move on and take a look at a question here. It says, calculating the amounts of reactants and products in a precipitation reaction. It says, magnesium is the second most abundant metal in seawater after sodium. The first step in its industrial extraction involves the reaction of magnesium 2+ with calcium hydroxide to precipitate magnesium hydroxide. What mass of magnesium hydroxide is formed when 0.180 liters of 0.0155 molar magnesium chloride reacts with excess calcium hydroxide? I mean, what's the first darn thing we got to do here? We got to come up with some kind of balanced equation, right? We're starting with what it's telling us is that we're starting with magnesium chloride, MgCl2, and we're combining it with calcium hydroxide. Right now, I've gone ahead and looked both of those up. They're both soluble. Now, what am I going to do? I'm going to end up doing a double displacement reaction. Let me move to the next slide where I have more space, and I'm going to rewrite that. Okay, so I'm going to start with magnesium chloride, which is aqueous. I'm going to combine it with calcium hydroxide, again, using the solubility table. I know that calcium hydroxide is soluble. Now I'm going to combine magnesium with hydroxide. So let's do that. I'm going to end up with magnesium hydroxide. Okay, like that. And I'm also going to end up combining what? Chloride and calcium to make calcium chloride. So let's write that out. CaCl2. Now again, I've gone ahead and looked both of these up in the solubility table. I already showed you how to use the solubility table. And we find that magnesium hydroxide is a solid and calcium chloride is in fact aqueous. It's soluble. The equation is already balanced. So here is my balanced equation. First part's done. Right, we've already solved the first part of this problem. Now it's telling us, or it's asking us, what mass of magnesium hydroxide are we going to get? Okay, so we're trying to figure out the mass in grams of magnesium hydroxide that we get when we react 0.180 liters of a 0.0155 molar solution of magnesium chloride. Well, you can see that the stoichiometric coefficients here in this balanced equation, right, is 1 mole of this will react with 1 mole of this to give you 1 mole of this and 1 mole of this. So everything's there is present in a 1-to-1 to 1-to-1 ratio, okay? So that means I can start my dimensional analysis like this. I've got 0.180 liters of magnesium chloride, and from my molarity, right, I know that there are 0.0155 moles of magnesium chloride in 1 liter of magnesium chloride. Remember, molar stands for moles per liter, right? Okay. If we were to stop right here, we would cancel out the volume of magnesium chloride, and we'd end up with the number of moles of MgCl2. But we want the number of moles of magnesium hydroxide. Where are we going to get that? We're going to get that from our balanced equation. We know that this is a 1-to-1 ratio. And I can use my balanced equation to write a beautiful conversion factor here. I know that for every 1 mole of magnesium chloride, I produce 1 mole of magnesium hydroxide, like that. I'm going to break this one up a little bit. Okay, normally I don't like to do this, but I'm going to do it a little bit. If we were to stop right here, you can see that liters cancel out, moles of MgCl2 cancel out. I haven't even done this because I don't like to break these up, but I'll do it just to try. So we have 0.18 multiplied by 0.0155. That gives us 0.00279. And then I'm going to multiply that by 1/1. So that's going to equal that I end up with 0.00279 moles of MgOH2. Okay? It's asking me for the mass in grams of magnesium hydroxide. Can anybody tell me what my next step would be? Not a trick question. Mr. Dion doth not like trick questions. What would I do next? If I've got the number of moles, somebody says multiply by molar mass. Absolutely. I'm going to multiply the number of, did I write grams in there? Oh, Mr. Dion's losing it. There we go. I'm going to write, I have the number of moles of magnesium hydroxide. I'm going to multiply that by the molar mass of magnesium hydroxide. Now, I've already gone ahead and looked that up. It's 58.33 grams per mole. So I know that I have 58.33 grams of magnesium hydroxide in 1 mole of magnesium hydroxide. Look at this. Moles of mag hydroxide cancel out. Punch all that beautiful spinach into your calculator, and you end up with 0.163 grams of magnesium hydroxide. Okay? Look, let's stop for a second. Let's take a break. Okay? It's 9:47. We've earned it. Okay? Look, everybody out there who can hear my voice right now, there is nobody who is hearing me right now that can't do multiplication, division, use a calculator. Everybody who's hearing my voice knows how to do that, right? There is no, we're not doing any calculus here. This is just easy calculator calculations, right? What's the difficult part of all this stuff in chemistry? What makes it complex is being able to interpret the problem and set it up correctly. Okay, that is what makes chemistry difficult. Being able to look at nomenclature, get everything all set up. If I was to ask you, okay, I want you to divide, I want you to multiply 0.18 and 0.0155. You're like, well, duh, yeah, I can do that. Give me a calculator, done, no problem. Okay, it's a matter of setting things up. And so that is why when you're studying chemistry, don't always just seek to get the right answer and then just like blow it off. Just, okay, got the right answer, moving on. Make sure you have a little bit of understanding. And I mean, I want to say a lot of understanding, but make sure you have at least some understanding of what the heck is happening. Okay, don't just start punching numbers into a calculator. Finally, you get the right answer and cheer. I mean, yes, in some cases maybe, but you want to make sure that you understand a little bit of what the heck is going on. Okay, and I'm not trying to say that to discourage you. I want to encourage you to just think about what you're doing, when you're doing chemistry. All right, I have the solution on the next two slides. This is the solution put forth by Madam or Dr. Silberberg herself. Okay, and then over here, if you went to the library, if you went to the Science Center back in the pre-pandemic days, you were able to take out books from the Science Center or read them in the Science Center at least. If you were to grab any first-year chemistry textbook, I don't care who the author is, they're always going to have some iteration of this slide right here. And you're like, didn't you say that another day? I probably did. Okay, but there are some slides that are just ubiquitous, that are in every chemistry textbook. I know that most of you probably grasped this concept already, but in case you don't, I want to run this by you one last time. You can't make a direct comparison between mass of substance A and mass of substance B in chemistry. If you're like, what do you mean? Let me back up and really get into the nitty gritty here. Look, if we go back to a beautiful, look at this, gorgeous balanced equation. You can see that the stoichiometric ratio is if I react 1 mole of this with 1 mole of this, I get 1 mole of this and 1 mole of this. What they're saying, where that big X is, that big giant red X, what they're saying is you can never pull this kind of shit. You can't say, okay, I got 2 grams of this, I'm going to end up with 2 grams of that. No, 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 no. That doesn't, chemistry doesn't work that way. What the balanced equation tells you is if you have 2 moles of this, yes, since it's a 1-to-1 ratio, you would get 2 moles of this, yes. So you always have, like somebody says, when in doubt, convert to moles. Hot diggity damn. I agree. All right, Aaron, when you're in doubt, convert to moles, okay? So how do you convert from mass to moles? Well, you use what? Big M, right? This is molar mass in grams per mole. What else? So then you would relate the amount of moles through what? Starts with B, ends with balanced equation. That's right, a balanced equation. Okay, what else can you do with the number of moles? Well, if you have a concentration, you can figure out the volume. If you know Avogadro's number, which you should have it memorized, right? Then you can figure out the number of entities, atoms, molecules, people, whatever, okay? So, I mean, the whole take-home message of this slide is really nothing that sophisticated. All it's saying is don't ever do this, okay? Don't ever try to do that, all right? And again, by the time I get to this point in the class, first exam is over, it's very rare that I would see a student try to pull that kind of thing. But just to put the bug in your ear, just so you're fully aware of what you can and can't do, you know, chemists love rules. All right, let's try another problem here. What's this problem about? Ooh, a limiting reactant problem. So this, look, a student sent me an email asking me about reaction tables, I'm never going to ask you to write a reaction table out. So I'm going to just ignore this part for now, okay? But we are very concerned about this, okay? They even have limiting reactant problems on the ACS final. So this is very important for us in Chemistry 1401. It says if you take iron 3 hydroxide, you can make it by reacting aqueous solutions of iron 3 chloride and sodium hydroxide. What mass of iron 3 hydroxide is formed when you take 0.15 liters of a 0.250 molar solution of iron 3 chloride and you react it with 0.215 liters of a 0.300 molar solution of sodium hydroxide? Well, the first thing that we need to do here is make a balanced equation, right? So I'm going to help you out with that. I obviously have it on another slide, but look, you've got to be able to come up with these, okay? It says here that you take iron 3 chloride, FeCl3, you react it with sodium hydroxide, and you make iron 3 hydroxide. What else would we get? We'd also get sodium and chlorine combining. So we'd also get sodium chloride. Then it's just a matter of balancing this equation. And so we have 3 chlorines. What do we got here? We got 3 hydroxides, so we're going to have at least a 3 here. Then we need a 3 here. And are we done? Yes. Okay. So we've balanced out our equation. All right. So I have that put on this slide over here. Now I'm going to walk you through the whole thing from soup to nuts. I don't know what this little line is here, but we'll just ignore it. This thing here, I don't know what that is. Anyhow, let's get to it and add it into it. So what it's telling us is that we're starting out with, look back at my notes here. I don't want to rifle between slides. Okay, so for iron 3 chloride, we are starting out with 0.155 liters of a 0.250 molar solution. And for the sodium hydroxide, I'll write it down here, we're starting out with 0.215 liters of 0.300 molar sodium hydroxide. Look, both of these, we have the volume and we have the molarity. Do you remember this formula that I told you the other day? That molarity is equal to the number of moles per volume. Okay, there we go. Good. That molarity is equal to the number of moles per unit volume. So that means I can rearrange that formula to get the number of moles is equal to the molarity times the volume. And so I'm going to use that formula, number of moles is equal to molarity times volume, to figure out the number of moles of iron 3 chloride and the number of moles of sodium hydroxide. Let's do just that, okay? So we'll start with iron 3 chloride. So for our FeCl3, we have 0.155 liters of FeCl3. We have 0.250 moles of FeCl3 in 1 liter of FeCl3. If I was to stop right here, you see that I would end up with moles of FeCl3. I'm not going to do that. I'm going to move over to the sodium hydroxide, and then I'll come back to this in a second. So for my sodium hydroxide, I do the same exercise, 0.215 liters of sodium hydroxide multiplied by 0.300 moles of sodium hydroxide in 1 liter of sodium hydroxide. Look, the volume of sodium hydroxide cancels out. If I was to stop here, I'd end up with moles of sodium hydroxide, but I'm not going to stop here. Let's go back to the iron 3 chloride. The question is asking us, what mass of iron 3 hydroxide are we making? We want to know the mass in grams. Well, the first thing we should do is figure out how many moles of iron 3 hydroxide would be produced from this amount of iron 3 chloride and all of the sodium hydroxide in the universe, and this amount of sodium hydroxide and all of the iron 3 chloride in the universe. This is the exact same kind of limiting reactant problem that we looked at earlier in this class. And so I'm going to use my balanced equation. I know that for every 1 mole of FeCl3, I make how many moles of iron 3 hydroxide? The answer is 1. It's a 1-to-1 ratio from my balanced equation. Now, when I punch all of this spinach into my calculator, I end up with 0.0388 moles of iron 3 hydroxide. Remember, this number might not be our answer, okay? This number, all this number tells us is if we started with this much iron 3 chloride and we ignored this, we just said we have all of the sodium hydroxide that we need, we have it in excess, okay? We would end up with this much. Now we need to do the exact same exercise for the sodium hydroxide. So I know that for every 3 moles of sodium hydroxide, I produce 1 mole of iron 3 hydroxide from my balanced equation. Now I'm going to put that into my dimensional analysis. So 3 moles of sodium hydroxide, I end up producing 1 mole of iron 3 hydroxide, like that. Now, this units are going to cancel out, and I end up with the number of moles of iron 3 hydroxide as being 0.0215 moles of iron 3 hydroxide. I have a question for you guys. What's my limiting reactant? What's my limiting reactant here? Is it iron 3 chloride or sodium hydroxide? Absolutely, sodium hydroxide, because it forms a lesser amount of iron 3 hydroxide. And so this is the maximum amount of iron 3 hydroxide I can make, and sodium hydroxide is my limiting reactant. Okay, what's the mass of iron 3 hydroxide I'm going to make? Well, I've already gone ahead and looked up the formula mass of iron 3 hydroxide, which is 106.87 grams per mole. So I take 0.0215 moles of iron 3 hydroxide, and I multiply that by my formula mass, which is 106.87 grams of iron 3 hydroxide in 1 mole of iron 3 hydroxide, like that. You can see that the units of moles cancel out, and when I do that, I should have 3 sig figs, shouldn't I? Why did I only put 2 sig figs? Let me get out the old calculator here. So 0.215, nope, 0.0215 times 106.87. There we have it, folks. You get 2.30 grams of iron 3 hydroxide. Cha. What the heck? Iron 3 hydroxide, not iron 2 hydroxide. There we have it. All right, another limiting reactant problem in the books. Okay. I find that this is the best way to do it. I don't find that the reactant tables are generally speaking, I don't find them very helpful for my students. So we're going to skip that part. We're going to keep moving. We've got, what, 2 hours left in lecture, lots of time. And let's talk about acids, bases. Does anybody know anything about acids and bases? Yes, what do you know? Tell me something about acids. Where's an acid that we would, what's an acid this is one of my favorite things. What's an acid that we would use in everyday life then, Violet? Let's see, I'm scrolling down here to read what my students have to say. pH levels, yeah, pH levels are a measure of acidity, sure, or can be used to measure levels of acidity of an acid. Acids have a hydrogen in it, yeah, okay. Some acids, not all acids. HCl, hydrochloric acid, yeah. All right, so my students know all kinds of things about acids. Never add water to acid. So in Audrey, in French, we say acide dans l'eau, bravo, which means acid in water, bravo. And then we say l'eau dans acide, water and acid, suicide, which is suicide. So yeah, good one. All right, anyhow, there we go. Well, let's talk about acids and bases. And we're going to start with a couple of definitions. Okay, so the first one is an Arrhenius acid is a substance that produces H plus ions, so hydrogen ions in solution. And when we have an H plus ion, we have a SATSI name for that. Okay, we just call that a proton. And you're like, what? A proton? Well, if you think about it, Okay, what is a hydrogen atom made out of, right? It's got one proton in the nucleus, so it's got one proton, and it has one electron, right? One electron. So if you remove that electron to make H plus, what have you got? You've literally got the one proton. And so that's why we call it a hydrogen ion. We call it a proton. Kind of cool, huh? Anyhow, an Arrhenius acid is a substance that produces protons or hydrogen ions when dissolved in water. So examples would be, here we have just some generic acid, HX. It could be something like HCl, could be something like hydrochloric acid, it could be hydrobromic acid, it could be hydroiodic acid. Yeah, so it dissociates completely into its ions. What else do we know about something that dissociates completely into its ions? Would that be an electrolyte or a non-electrolyte if it dissociates completely into its ions? Yeah, if it dissociates into ions, it's an electrolyte. Absolutely. Yes, a strong electrolyte, right? An Arrhenius base is a substance that produces hydroxide ions when dissolved in water. So if you take some kind of metal hydroxide, the metal, not always, but the metal is usually a group 1 or group 2 metal. So what are the group 1 metals? Lithium, sodium, potassium, rubidium, cesium, group 2, magnesium, calcium, strontium, like that, okay? It's usually one of those, and if it's a hydroxide, it breaks apart. So hydroxides, right? If you form hydroxide ions when you dissolve in water, that makes you a base, all right? So we've defined what acids and bases are. And when we take an acid and a base and we mix them together, we get what's called a neutralization reaction. So if you were to take an acid like hydrochloric acid, I'll just help you out a little bit here, hydrochloric acid, and combine that with a strong base like sodium hydroxide, I wouldn't recommend doing it. But if you were to do that, what you end up with in this neutralization reaction, right, because this is an acid, this is a base, you end up producing water as one of the products. Water is a liquid. And you would also produce sodium chloride, which is an ionic solid, which would be, so in solution. And so normally, or not normally, but oftentimes we produce water and a salt. Not just table salt, but a salt, okay? So that's usually what happens in a neutralization reaction, is that you end up producing water and a salt from an acid and a base. All right, neutralization reactions. What's an acid? Something that makes hydrogen or protons in hydrogen ions or protons in solution or when dissolved in water. And an Arrhenius base is something that when you dissolve it in water, it makes hydroxide ions. You mix an acid and a base and you get a salt plus water most of the time, not all the time. What else? It says here that hydrogen ion or the proton ion or the proton is a solvated hydronium ion. Well, there's some good information about this in the textbook. But if you think about water, okay, and I've mentioned this before, that there's a reason why we draw water with this bed shape, and we'll look at it later on in the class. But water, the oxygen atom in water is much more electronegative than the hydrogen atom. And electronegativity, what that means is that oxygen has an ability to pull electron density towards itself in the molecule. And so it's not an anion, but it's the oxygen is like partially negative. And that renders the hydrogens partially positive, right? So what happens is that partial negative in that oxygen, that can actually interact with that tiny little proton, and it actually binds to it. And what we end up forming is H3O plus. So here we have our oxygen, and it's bound to 3 hydrogens like that. Okay, so we form H3O plus. I'll help you out here. H3O plus. Okay, it's got a lone pair and a positive charge, and we'll talk more about the structure later on in the class. But I want you to know what this ion is called. So H3O plus, that is called hydronium. Hydronium. Okay, so a hydronium ion. It's a polyatomic ion that you have to know moving forward. All right, other things that you need to memorize are the strong and weak acids and the strong and weak base, okay? Weak bases. Now, strong acids, there are 6 of them that you've got to know off by heart, all 6 of these. Hydrochloric acid, hydrobromic acid, hydroiodic acid. You probably noticed that chlorine, bromine, iodine, those are all halogens. So it might be a knee-jerk reaction to say, well, fluorine, isn't that a halogen? Well, in fact, HF, hydrofluoric acid, is a weak acid. It's a lot more dangerous to work with than any of those other acids. I wouldn't work with it if I didn't have to. But HF is, in fact, a weak acid. Other strong acids that you have to be aware of are nitric acid, sulfuric acid, and perchloric acid. Now, I know you learned the names earlier on when we studied nomenclature, but you also have to know that these three are strong acids. So those are the strong acids. Now, when it comes to weak acids, I mean, there are piles and piles and piles of weak acids. Ones that you should be familiar with, I think, the best ones would be HF, okay? Hydrofluoric acid is a weak acid. Phosphoric acid, sometimes students will fall into the trap and think that's strong. It's actually weak. And acetic acid. So somebody pointed out earlier on, vinegar, right? So the acid that's found in vinegar is actually acetic acid. Now this is called a structural formula right here. It gives you some information about how the atoms are connected. This is another way of representing it, but what's acetic acid made up of, okay? Based off of these two formulae that I have highlighted in yellow. It's got 2 carbons, it's got 4 hydrogens and 2 oxygens, right? And if you're like, well, why did they put the hydrogen off to the side here? It's just to show you that this is the acidic proton in acetic acid. Anyhow, I've talked about that too much. Let's move on and talk about strong bases and weak bases. So strong and weak bases, you have to memorize the strong bases. It looks really intimidating when you first gawk at it. You're like, oh man, that's too much, okay? But for group 1A, you just have to know lithium, sodium, potassium, rubidium, cesium, not francium. And you have to know for group 2A, just look at the periodic table, calcium, strontium, barium. They're all coming one after another. So not magnesium hydroxide, it's not a strong base. Anyhow, now, so you have to have those memorized. Now, this is something that Dr. Diaz, put in here one time. He said weak, one of many examples. There are thousands of examples, literally thousands of examples of weak bases out there, more than that, probably millions, okay? One that you should be familiar with is ammonia. Okay, ammonia is what's found in Windex, for example, and many other household cleaners. So ammonia, you should know the common name, ammonia, and you should know that it is a weak base, okay? And again, I know I say this to you all the time in chemistry class, but I just want to encourage you that if you find nomenclature and memorization difficult, if you find it challenging, and some students do, sometimes some students don't find it as challenging, look, never be discouraged with the time you spend memorizing things in chemistry, because these strong acids, strong bases, weak acids, weak bases, this is going to be handy. I promise you, for the rest of this class, it's going to be useful. Many of you are interested in taking chemistry 1411 in January. That's general chemistry 2. I promise you it's going to be useful then. Look, I don't promise anything, okay? I told my wife on our wedding day, this is a 3-year commitment. All right, look, I don't promise things to people, but I can promise you that in 20 years, if you come back and find me at UCCS, and I'll still be here, okay, the strong acids and the strong bases and the weak acids and the weak bases will not have changed. Okay, it'll be the same old ones. Good? Okay, so don't ever think you're wasting your time on that. Memorizing, the things that we get you to memorize in chemistry is always time well spent. Well, let's talk about acids and bases as electrolytes. Well, look, if we go all the way back to our strong acids and strong bases, we said that they dissociate completely. And the way that we represent that complete dissociation is by an arrow going in one direction, okay? That means it's dissociating completely, and that will produce a strong electrolyte. So let me give you an example. If you take sodium hydroxide, okay, and it's aqueous, well, sodium hydroxide is a strong base, right? Sodium is a group 1 metal. We end up with sodium plus and hydroxide minus, okay? These are both aqueous. I should have written that in there, okay? But this is complete dissociation, right? So we have ions, so this is going to be a strong electrolyte. The same thing applies to hydrochloric acid. Look, it's a strong acid. It's going to dissociate completely into protons and the chloride ion. Okay, complete dissociation. Again, it's going to be a strong electrolyte. Now, if I have something like a weak base or a weak acid, okay, they're going to be weak electrolytes. Let me give you an example. So let's try acetic acid. So acetic acid, if you don't remember, acetic acid was this, okay? You have CH3COOH, okay? Instead of complete dissociation, we get very little dissociation, and the way that we represent that is with an arrow going in two directions, like this, okay? It's not this. It's not a double-headed arrow and a double-headed arrow. It's an arrow with one barb and another arrow with one barb, okay? Like that. So it's going to dissociate partially to give us this oops, I'm missing the carbon, CH3COO minus as the anion and a proton, right? This is called acetate. This is one of the polyatomic ions that you had to memorize. Okay, but that's going to be a weak electrolyte. What about ammonia? I'll just kind of give you this one quickly. But ammonia, if you're like, there's no ammonia, there's no hydroxide in ammonia, because what happens is ammonia actually reacts with water, okay? And it takes a proton from the water to give you the ammonium ion, okay, plus a hydroxide ion, okay? I'm going to talk about that more later on in the class, but I just want you to know that since these are partial dissociations, they are, where is it, weak electrolytes, okay? That's the whole point. I put this beautiful diagram in here, this beautiful picture that somebody took the time to take, and I didn't even talk about it. I talked about it last class, I think, okay? So if you have a strong electrolyte, what's going to happen? The bulb is going to light up perfectly well. This is an experiment you can do really easily. I've done it in the lab several times in nursing chemistry. And look, if you have a weak electrolyte, it's going to conduct a little bit of electricity. Light bulb, not so bright. Anyhow, kind of fun. Has anybody done this experiment in the lab? Maybe in high school? No? Matthew, no? Okay. Well, I can tell you that I've done it a number of times, maybe 10 times or something in my life with different classes. So it's a fun and easy experiment. And what else is kind of cool, I'll just throw this bug in your ear, is if you take, like, let's say you take a strong, and I'm not going to ask you about this on the next exam. This is just for fun. Sometimes we're allowed to have fun in chemistry, right? If you take a concentrated solution of HCl, and you see that it conducts electricity really well, right? Because it's a strong electrolyte. If you lower the concentration, if you keep diluting it and diluting it and diluting it, eventually it's not going to conduct electricity. I'm not going to tell you that, Matthew. You're going to have to figure it out yourself if you want to do it. All right. So let's move on and take a look at a problem here. It says, determine the number of protons or hydroxide ions in solution. So how many hydrogen ions or protons are in 25.3 milliliters of 1.4 molar nitric acid? Hey, I'll just ask you right, just flat out, is nitric acid, is that a strong acid or a weak acid? Not a trick question. We looked at it earlier today. Strong or a weak acid? Nitric acid. What do you think? Strong. Thanks, Deona. Yeah. You guys ever heard of aqua fortis? Aqua fortis, not aqua velva. aqua fortis. Okay, I think it's like an old term for nitric acid. The pioneers or whatever, they used to take aqua fortis and they would put it on gun stocks. If they made a gun stock out of something like curly maple, and then they would put the aqua fortis on it, and they would bring out the grain in the wood to make it more beautiful. Anyhow, kind of some interesting history here. Okay, so how many hydrogen ions are present in this much nitric acid? Well, we've already decided that nitric acid is a strong acid. So look, if we take some nitric acid, HNO3, okay, aqueous, it's going to dissociate completely, right? Because it is a strong acid. Okay, and what's it going to dissociate into? H plus ions and nitrate ions, like that. Okay, because it's a strong acid. So that tells you that for every 1 mole of nitric acid, I make 1 mole of hydrogen ions and 1 mole of nitrate ions. Hey, well, that's pretty handy. Excuse me. Because I can figure out the number of moles of nitric acid because of this chestnut here, the molarity was equal to the number of moles divided by volume. Well, looky, I have the volume and I have the molarity. So I can rearrange that formula. N is equal to molarity times volume. All right. And since I know that these are in a 1-to-1 ratio, I'll know the number of moles of hydrogen ions. Let's do the math over here. Okay. Again, I'll rewrite the balanced equation. So we have our nitric acid, strong acid, dissociates completely into hydrogen ions and nitrate ions, like that. I'm starting out with 25.3 milliliters of this, okay? And I've been given the molarity, which is what? 1.4 molar. So 25.3, and it's 1.40 moles per liter. Can you guys convert 25.3 milliliters into liters in your head? Okay, so you would divide by 1,000 to get liters. Okay, so you'd move the decimal over 1, 2, 3. So you start it with 0.0253 liters of nitric acid, and I know that in 1 mole of, 1.4 moles of nitric acid. I have 1.4 moles of nitric acid in 1 liter of nitric acid. Look at my beautiful dimensional analysis. Volume of nitric acid cancels out. Where am I going to get the ratio of nitric acid to protons or hydrogen ions? From my, starts with B, ends with balanced equation, my balanced equation. So let's pencil that in. I know that for every 1 mole of HNO3, I form 1 mole of protons or hydrogen ions. And that's the question, right? It says, oh no, it wants how many hydrogen ions. That would be how many moles of ions we have, mole of hydrogen ions. And we know that in 1 mole of H plus, we actually have Avogadro's number of ions, 6.022 times 10 to the 23 H plus ions. And so you can see that moles of H plus cancel out moles. And we end up with, I've already done the math on this, you end up with 2.1 times 10 to the 22 hydrogen ions, like that. Good. All right. I noticed in my notes here I have a star by this. Must mean it's important. Okay. Maybe there's a question like this on the midterm. Wink, wink, hint, hint, nudge, nudge. Okay, strong acids. So here's the solution as put forth by the fearless author of our textbook. Let's look at some more problems. We got 20 minutes. Da, 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 da. Who's enjoying acids and bases thus far? Just me? We should try some more net ionic equations. I think that's what we should do. Yeah. Let's take a look at this. Violet, Dayhona, good. I like it. Heck yeah, me too. Da, da, da. All right. Yeah, acids and bases is always kind of a fun section. Look, I'm not trying to scare you or anything, but acids and bases, for some reason, is usually one of the more challenging things for students in chemistry. It's one of those things that I would say that, you know, eventually you will just get it if you keep working at it, but it takes a little while sometimes to figure it out. Let's try one of these problems, and then we'll move on to a different subject, the subject of titrations. It says here, write a balanced molecular, total ionic, and net ionic equation for each of the following acid-base reactions and identify the spectatorions. Let's just start with this one right here. This would be fun. Hydrochloric acid plus potassium hydroxide. What's hydrochloric acid? Well, it's HCl, AQ. What's potassium hydroxide? It's KOH, AQ. Remember that if you just write HCl, that's not hydrochloric acid, okay? HCl is actually a gas at room temperature, so that's hydrogen chloride, hydrogen chloride. Hydrochloric acid is what you get when you put hydrogen chloride in water, okay? So hydrogen chloride is a gas, and hydrochloric acid is an aqueous solution of hydrogen chloride in water. Okay, so now that we've got those two, we're going to end up with a salt plus water. So I've got it all written out on the next page. We're going to end up with potassium chloride and water. How did I figure that out? Look, all I did was I said, I've got a hydrogen ion. I'm going to combine it with the hydroxide. That's going to give me water. I've got a chloride anion and a potassium cation here. I'm going to combine those, and it's going to give me potassium chloride. That's all I did, okay? So there's my molecular equation. Now remember, we can only break up things in our total ionic equation. So now we're going to do the total ionic equation. We can, and I'll write it in here, only break anything that's aqueous into its ions, okay? And the reason I highlighted that is because water is not aqueous. Water is a liquid. Water is not an electrolyte. Okay, water is not an electrolyte. So we're not going to break water up into its ions. Now, let us proceed with our total ionic equation. From HCl, we're going to get one hydrogen ion, or one proton, plus one chloride anion. From our potassium hydroxide now, we're going to get a potassium cation, aqueous, plus a hydroxide anion, aqueous, which produces potassium chloride. That's an aqueous salt. So let's write that. We get one potassium ion, aqueous, plus a chloride anion, aqueous. And then my water, again, it stays intact. It is not an electrolyte. So H2O, liquid like that. Now for my net ionic equation, I'm going to cancel out all the spectator ions. Who could tell me what the spectator ions are in this reaction? Yeah, potassium and chloride. Absolutely. So if we look here, you can see that the chloride remains unchanged and the potassium remains unchanged. And so our net ionic equation, what I did there, our net ionic equation would be H plus OH minus, and I should put gives you water. So really what's happening in an acid-base reaction is that a proton, a hydrogen ion, is combining with a hydroxide anion to produce water. That's your net ionic equation. All right. Let's see here. There's the solution to that one. And this is the solution to the other one. We have strontium hydroxide and perchloric acid. And you can take some time and look at that. But when you write out the total ionic equation, you see that, look what cancels out. You see that strontium cancels out. You see that perchlorate cancels out. And you end up with 2 hydroxides plus 2 protons give you 2 moles of water. And you can simplify that too, right? You divide the whole thing by 2 and you end up with, look, it's the exact same net ionic equation that we saw right here, okay? There we go. So with an acid plus a base, oftentimes the net ionic equation is going to be just a proton plus a hydroxide gives you water. All right, this slide just kind of shows you the proton transfer process. So you have your strong acid, you have your hydronium ions, and your halide maybe, and then the proton gets transferred over to the hydroxide to make water. Anyhow, there's nothing really there that I can tell you that's new. With that in mind, let's see here. This whole thing, so on account of the pandemic, I've told you before that I would try to distill chapters into the simplest possible bits. This thing here where it says use curved arrows, I won't be asking that on any exams or midterms, and it's not on the ACS final. In fact, I don't find it's all that useful until you get to organic chemistry to be able to do that. But do you guys want to try one more? Writing out a net ionic equation? Or do you want to move on to titrations? Okay, Kenner says yes, please. So let's do it. Let's give it the old college try here. It just says write the balanced total and net ionic equations for the reaction shown below and show how the proton transfer process. Okay, anyhow. And also, there's another cool part down here. It says, give the name and formula of the salt present when the water evaporates. Look, let me show you what's going on here. we're taking hydroiodic acid. What's that? It's HI, aqueous. We're combining it with calcium hydroxide aqueous. What's that? CaOH2, aqueous. What are we going to get? We're going to swap, right, the ions so that we're going to end up with calcium iodide, which is soluble from the solubility table, plus water, which is a liquid. Water is never aqueous. Is this a balanced equation? The answer is no, it's not. I got to have 2 here. 200, so that's 4. I'm going to have 2 here. It's okay. I think it's balanced now. So now that I have balanced out the equation, this is my molecular equation. Now it said here we need a total and net ionic equation. So let's write our total ionic equation. So everything that's aqueous, we're going to break it apart into its ions. So we've got from our HI, we've got 2 moles of that. So we've got 2 H plus ions plus 2 I minus ions, iodide, plus Ca, calcium, 2 plus ion, plus 2 hydroxide. So we're going to put that 2 up here just so that we have 2 of those. We produce calcium iodide, so we have Ca 2 plus aqueous, and we have 2 iodides, so plus 2 iodides. And remember, water is not an electrolyte. We just put plus 2 H2O liquid. Now, for our net ionic equation, before we do that, we're going to cancel out all the spectator ions. So we've got calcium cation doesn't change, and the iodide anion doesn't change. What's left over? We've got 2H plus 2OH minus gives us 2H2O. We can simplify that if we divide everything by 2. First, I'll write it out. 2H plus aqueous plus 2OH minus aqueous gives us 2H2O liquid, right? We could divide all that and put H plus OH minus gives us what? Water. Look at that. For the 3rd time, we get the same net ionic equation from the combination of an acid and a base. All right, so neutralization reactions, acid, base. There we go. And there's the solution. All right, well, let's finish up. Let's spend the next 2 hours talking about acid-base titrations. Has anybody here ever done a titration before? Something that some of you may have done before in another chemistry class. Somebody says yes, yes. Okay, somebody says no. Okay, so we got a mixed bag. Some people have, some people haven't. Well, look, Matthew, if you plan on taking General Chemistry 2 with me in the spring, and I hope you do, if you take that lab simultaneously, so that would be Chemistry 14-12, I think in that lab, you probably do like 10,000 titrations. I mean, I'm kidding, but it's like titration after titration after titration. So you spend a lot of time doing titrations. Look, if I had to explain this, a titration to somebody on the street, like if somebody on the street that didn't know anything about chemistry said, what's a titration? I'd say a titration, if you have a solution of an acid, okay, you have an acid and you don't know the concentration of that acid. No idea what the concentration is, okay? Somebody on the street, I'm really spending some time on the street here. Anyhow, somebody on the street just hands you a bottle of, it says acid, okay? It's HCl, okay? And you don't know the concentration. You're like, man, is this 6 molar? Is this 0.1 molar? Like, am I going to get hurt by this, you know, if I spill it on myself? You can figure out the concentration of an acid by using a base that you know the concentration of, okay? So what you need to know are the concentration of the base, and you can do the technique of titration, and you can determine the concentration of the acid that you don't know the concentration. How can you do that? It's all based on this formula here. That concentration is equal to number of moles over volume, right? Because in a neutralization reaction, right, between an acid and a base, we can write out any neutralization reaction and we can determine the ratio of moles of acid to moles to base. Now let's see here. Before we get into the nitty gritty of it, the nuts and bolts, let's go over some definitions. It says here a titration. In a titration, the concentration of one solution is used to determine the concentration of another. That's the definition of what the heck a titration is. In an acid-base titration, which is one of the most common types of titrations, you take a standard solution of a base, and when it says standard solution, like standard to what? Okay, standard is a sassy way that we say solution that you know the concentration of, okay? The concentration of. So let's say you had a base, sodium hydroxide, and you knew the concentration, 0.1000 molar. There you go. Good. Okay, and it's usually added to a sample of an acid of unknown molarity. Then we use what's called an indicator. So we do the acid-base reaction, and we have an indicator that has different colors in acid and base, and then we use that in our naked eye to monitor the color of the reaction, and we can tell when we're finished the titration. At what's called the equivalence point, okay, the number of moles from the acid are going to be exactly equal to the number of moles of hydroxide produced by the base, right? The neutralization reaction, right? H plus OH minus gives you water. Okay, cool, cool. Well, if you add just a tiny bit more of the base to the titration flask, and I'll show you what that means in a second, you're going to have a little bit extra base. And when you have a little bit excess of the base, it's going to react with the indicator and cause it to change color permanently. Okay, so when you see the color change, you know the titration is over. You have the volume of the base, you know the concentration of the base, you can figure out the number of moles. You have the balanced equation, you figure out the number of moles of acid, you know the volume of acid. Number of moles of acid divided by volume of acid, boom, concentration of acid. I said that pretty quickly. So let's take a look at a picture of what an acid-base titration looks like, okay? You have an instrument called a burette. So this is called a burette, okay? It doesn't show you the whole thing here. But in the burette, you have your base, okay? So this is a base, hydroxide, right? This is your base. And you can measure the volume with a burette, okay? Burettes actually measure volume very accurately. Now, in here, you have your acid. You don't know the concentration, but you put in a volume that you know, right? So you know the volume, but you don't know the number of moles. Well, hold on. How can you figure out the number of moles of acid? Look at your balanced equation. Once you reach the equivalence point, okay, and the end point, the number of moles of hydroxide that you added from here are going to be equal to the number of moles of acid. Ah, now I see what's going on, okay? So you add sodium hydroxide or your hydroxide base very slowly, and you can see how it's a little bit pink down here. What you would do is you would pick that up with your hand, okay, and you would swirl that around, okay? You'd swirl that around until it goes clear again. Then you keep adding base, okay, until the pink color stays. You want a slight excess of hydroxide. And that's called the end point, okay? And you assume that the end point and the equivalence point are the same, okay? So you assume that the number of moles of OH minus that you added here are the same. And you're like, well, they might not be exactly the same. Well, they're close enough that you can make that assumption, okay? So again, to rehash, and this is the third time I'm saying this, okay? You know how much base you added. You get the volume of base from here. You know the molarity of the base, okay? So that means you can figure out the number of moles of base, because number of moles of base is going to be equal to the molarity of base times the volume of base. Okay. Now you know from your balanced equation, if it's a 1-to-1 ratio, like in here, you know that your number of moles of base is going to be equal to your number of moles of acid. Now you can take that number and plug it in here, and you figure out the molarity of your acid. All right, give me a thumbs up if you even follow me on what the rationale that I'm saying here is. Because it's a lot of talking. Good, okay, all right, even if a few people understand. Because I'll tell you what, the best way to understand what's going on in a titration, I think, is to try some problems that involve acid-base titrations, okay? And so these are just some pictures of somebody doing titrations. I don't know who it is. They really have some big lab coat sleeves. Anyway, you can see them adding the titrant. So the base is called the titrant slowly. By the way, I'll just say one thing since most of you, I'm not your lab instructor. I'll just tell you one thing. Titration is a one-person activity, okay? It doesn't mean you can't work in pairs, but you see both of these hands, they're both attached to the same torso, okay? There's nothing that breaks my heart more than when I peek my head into the lab and I see one student with their hand here on the stopcock and the other person swirling the flask. That's not how it works, okay? Look, both of these hands, that looks like two different hands, doesn't it? Or is that the same hand? No, those are the same hands. You can't see the sleeve here. Anyhow, I'm doing some investigative work here. Anyhow, it's a one-person thing. Anyway, where was I? It's 10:38. Why don't we stop there? And next class, we'll just look at a titration problem. Again, I would recommend that this is general chemistry. You try the problem, and we're going to look over this problem. And once we finish this problem on Monday morning, we'll take a look at this. And then we're going to bounce right into chapter 14. Can I give you a little warning about chapter 14? You're like, Mr. Dean, I'm sick of your warnings. It seems like all you do is give us warnings.